Okay, hi everyone. This is the first video of the ninth week, and actually the only video of this week, because if you remember, according to our schedule, there are supposed to be no lectures or labs this week because we had holidays on Monday. Next, regarding your homeworks, so far I have looked at the first couple of exercises in homework 1, and I'll try to look at the rest in the following days so that you finally get your results. Next, homework 2 was due on Monday, while late days expire on Friday, and so far I believe that 29 people already submitted homework 2. And finally, homework 3 will, according to the schedule, be out next week. Okay, so the only thing that is left for this video is to discuss the 5 networks challenge. Thank you all for submitting your solutions. More people submitted to this challenge than for any of the other challenges before, which is great. And if you remember, you were given 5 networks: Flickr affiliation network, Actors collaboration graph, an example of a web graph, a sample of citation network, and a realization of an Erdős-Rényi graph. And you were supposed to distinguish between these networks based on their structural properties. Most students correctly identified 3 out of 5 networks when they swapped the last 2. There are some examples of people where they got exactly that identified all 5 networks correctly. However, in most cases, I was not really satisfied with the reasoning that you provided. Why is that? For instance, most of the people distinguish random graph from the rest by plotting the degree distribution of all the networks and trying to see which one roughly follows Poisson. Which is completely okay, but as you will see that we can distinguish between the networks much easier without doing any plotting and so on, just to compute a couple of statistics. Then, in a lot of cases, your reasoning was not really robust. It was based on some assumptions that would not necessarily hold in general. I could give you more nasty examples of these networks where your reasoning would fail. And in particularly, a lot of people in your reasoning you write, I would assume this or that, or probably it holds, or it's more likely this or that, which is not really some robust reasoning. I'm sure I can find examples of the same type of networks where your reasoning will fail. Further on, more than one person actually flipped a coin to distinguish between at least 2 networks, which is obviously not a robust solution. You have a 50-50 chance. So, if I tell you how I intended to distinguish these networks in 2 steps, as I already said. So here I have all these 5 networks. And I first decided to compute the clustering coefficient of all the networks. So the values that I get are 0.25, then 0.00003. Then for the third network I get exactly 0. Then 0.08 for the fourth network, and finally 62 for the last network. And looking at just these values, you should already be able to distinguish 3 networks. Firstly, what would be the clustering coefficient of a random graph? we know that the expected clustering coefficient is the density of the graph, so the parameter P of the Erdos-Schreding model. So it's something super, super small, however, not exactly zero. Because probability that no triangles will form in a network of size almost 200,000 is practically zero. So I can immediately see that the second network is the random graph. Next, I get the value of 0 for the third network. Which one is that supposed to be? This is obviously the Flickr affiliation network. Why? Because any affiliation network is actually a bipartite graph, meaning that there is a division of the network into two groups where there are no links within the groups, meaning that there can be no triangles there. There are no triangles in affiliation graphs or in bipartite networks, meaning that the third network must obviously be the Flickr network where the clustering coefficient should be zero. Finally, let's look at this last value, 0.62. Which network should have the highest clustering coefficient? And if you think about that, should obviously be the actors collaboration graph. Why? Because this is actually a projection of a bipartite graph, of a bipartite network. When you have actors on one side, movies on the other side, and then you project on the actor side. Each movie then obviously will be a click in the projected network, and the entire collaboration graph is basically just a union of clicks. So it will have a substantially high clustering. Many of the people reason that the last network is the collaboration graph correctly because it has the highest degree. Which only holds in this particular case. I can give you examples of collaboration graphs that have lower average degree than some other networks. However, their clustering coefficient will still be substantially high. So I can get that the last network is the collaboration graph. So I am only left with two other networks. What is a nice property also, that both of these two networks are actually directed networks, are directed graphs. Many of you distinguish between undirected networks and directed networks by simply looking whether you will find a link that goes in both directions between the, node 1 and 2 and 2 and 1, for instance, which could not happen in an undirected graph because I told you that I reduced all the networks to simple graphs. This is probably, of course, not the wrong reasoning. In the following years, I will correct these networks so that all will look like simple graphs even in the undirected case. Hopefully that I will not destroy the structure of the networks too much. But with our reasoning, just looking at the clustering coefficient, I can distinguish which two networks are directed. Now, how to distinguish between the remaining two networks, so the web graph and the citation network? I don't think that anyone did this last step that I intended, and the idea here is to compute the size of the largest strongly connected component in these two networks. Because now I know that these two remaining networks are directed, I can treat them as directed graphs, I have the concept of strong connectivity, and I can compute the size of the largest strongly connected component. And the results that I get is that the size of the largest strongly connected component in the first graph consists of roughly 35,000 nodes, which is 18% of all the nodes in the network. Whereas in the fourth example, the largest strongly connected component consists of only 12 nodes, which is close to 0%. And with this information, I immediately know that that has to be a citation network. Why is that so? Because in contrast to the web graph, the citation network is actually a temporal network, meaning that it has some temporal time structure, because when new papers arrive, they can only cite papers in the past. Meaning that in theory, this network should be a directed acyclic graph. There should be no cycles there, because you can only cite papers in the past. Due to some errors in the data, or cases when you would cite a preprint paper on archive, for instance, that appeared in the past, but then this paper is published in a journal at some point in the future, and this link is corrected in the bibliographic database, so you might still expect to have some short cycles there, but not many. So looking at the results, you can immediately see that since the largest strongly connected component in the fourth network consists of practically no nodes, that this has to be the citation network, and we are only left with the first network, which the only one that remains is the web graph. And this reasoning that I have just given you, it's a very robust one. I mean, it does not, it's not based on any assumptions about how these networks should look like. It's only based on their structural properties of how they were constructed. This is basically it. So everybody who submitted and got at least 3 networks right got a plus. If you got more networks right, you get more pluses, and so on. And I also looked at your reasoning, that it should have as little mistakes or unrobust reasonings as possible. So that is it for this week, and see you in the 10th week. Thank you for listening.